what was sort of covered the last time. And by last time here, I posted a video lecture, and then Kevin kind of did a bunch of this stuff in like a recitation section, like kind of during the lecture time. Kevin's super good at this stuff. He's like probably one of the best people you could ever meet to talk about this kind of stuff. So you were in good hands for that. I'm going to kind of like recap some of that stuff now, ease us back in because it's been a while, and we're going to kind of talk about some more of this stuff. So in the lecture content, between the lecture content that I posted and the stuff Kevin talked about, there was sort of this kind of like deterministic optimal control sort of, I don't know, recap summary thing. And then I kind of went through a little bit of like kind of almost decision tree for like how to decide what sort of methods to use for sort of LQR versus MPC for, say, tracking problems or stabilization problems, and then DDP versus direct collocation for nonlinear trajectory optimization, and try to give you like a list of pros and cons and maybe when you would use one versus the other. And hopefully that kind of helps you map out some of these algorithms and, you know, when you might choose to use one over the other kind of thing. Okay, so that was that. And then there was a whole bunch of sort of content on quaternions and attitude, and Kevin did a whole separate thing on that stuff. So hopefully you got a healthy dose of that, and like some of that sticks in your brains from like a week and a half ago. But knowing how, you know, things are, I'm going to sort of recap a bunch of that stuff now. So to be clear, yeah, all this quaternion stuff, this attitude stuff, this isn't necessarily like a classic optimal control topic, but it's very much a robotics and like aerospace topic that's super, super practical and useful anytime you want to do floating base anything. So we're talking about drones, underwater vehicles, even cars and quadrupeds to some extent, like anything that's not like bolted to the ground industrial robot, this sort of stuff comes up, and you'll see lots and lots of terrible ways of dealing with this, namely Euler angles, cough, cough, don't do this ever, it's bad for you. So this is like the right ways to deal with this stuff. And the intersection of this kind of topic with optimization and sort of in particular control, right, is very, very sort of core robotics thing that's a bit more on the applied side of the discussion, but I think is really relevant to hopefully stuff you guys are checking out in here. So we're going to spend some time on it. It's also a major like pet peeve and a thing for me when I go read papers and see people use like hacky Euler angle stuff. So all kinds of badness happens. Yeah, so that Euler angles are bad for you. Don't use them. Do this instead. That's the quick summary. The other one to take away from this class, right, is don't use Euler angles. Don't use Euler integration for simulation either. Right, the Eulers, steer clear of those Euler things. Okay, so today what are we going to do? So we're going to really go deep on this quaternion topic and talk about optimization with quaternions in the mix. And so this applies pretty broadly. So today I'm going to give you like this pretty high level discussion of just like optimization with quaternions. The tools we're going to develop today are equally relevant across, you know, online control, LQR, nonlinear trajop stuff with like DDP or Dirkall. Also relevant to things like state estimation. In fact, like these tricks are super common in like standard EKF type stuff for state estimation. Huge array of things. It's a very like core robotics set of ideas that you should know about. So I don't know. That's why we're doing it. It's good for you, even if it's a little off the beaten path from like the classic optimal control thing. Okay, cool. So let's do a little kind of quick recap. So this is stuff that definitely should have gotten, you know, was covered in like the video I posted, and Kevin went over it in his like recitation thing. So I'm just going to do a real quick recap. Again, go watch that stuff. And if you have questions with it, this stuff is kind of tricky to wrap your brain around a little bit. It's weird. It's sort of, you know, stuff that you typically don't learn about till grad school. So, you know, it takes a couple of rounds of seeing it, and you got to really wrestle with it a little bit. Okay, so to summarize, these things, you can think of them as 4D unit vectors. They more or less act like rotation matrices most of the time. You can think of them that way in a lot of contexts. They have a multiplication rule where I can take two of these guys, say Q1, I'm going to write multiplication using like that star kind of notation. And these guys have a scalar part and a vector part. And in terms of the scalar and vector part, we can kind of write this down in terms of classic like vector dot and cross product stuff that you know how to do. So there's the scalar parts multiplied together, and then the dot product of the vector parts. And then down here, we've got something that looks like basically like a generalization of the vector cross product. Cool. So that, everyone saw that last time, dots and cross products in there. Like this is a weird, basically a weird mashup of both the dot and cross products from like classic vector algebra. In fact, this is older than those ideas. And Gibbs, when he invented like standard vector algebra, like did it as a way of like simplifying this stuff, which is kind of a weird aside. Okay, so then that's like the, the standard stuff. We kind of invented some extra notation here for doing calculus, which we'll see in a second when we start doing optimization. So we're going to write this down. We're going to define these L and R matrices. Here's the L one. It looks like this. It's a 4x4 matrix. And we're going to define these guys such that we can rewrite this quaternion multiplication thing as a matrix vector thing. So we've got this Q1, Q2. This is going to be L of Q1 times Q2. This lets me write this as like a matrix L times Q2, just like treat it as a vector. The reason we're going to do this is so that when I want to go take a derivative of, say, Q1 times Q2, if I want to take that thing's derivative with respect to Q2, it's L of Q1, right? That's where we're going with this. And then similarly, we can define an R matrix such that this guy's R of Q2 times Q1. That's the same idea. You're just going to look up there, pull out all of the Q2 bits and put them in a 4x4 matrix. So we're defining these this is like literally so we can take Jacobians of this stuff. That's why we're doing it, right? Okay, cool. So we got this stuff along these lines, right? Basically, I'm going to write all this quaternion algebra stuff in terms of a handful of matrices. And again, I'm doing that so I can do normal matrix vector math and take derivatives, basically so I can compute Jacobians of this stuff. Okay, so that stuff. Then we got this thing called the quaternion conjugate, which is the equivalent of the transpose for a rotation matrix. So it gives you the opposite rotation. We write it with a dagger superscript like this. And all you do is negate the vector part of the quaternion. So we're going to write this also in a matrix vector kind of way with, we're going to invent this matrix big T. So that it just, again, this matrix is defined such that it does the conjugate. And if you kind of think about that for a sec, it's sort of obvious that this needs to be a 4x4 matrix with a 1 and then a negative identity, right? So it flips the sign on the vector part. Nothing magic here. I'm just making stuff up to make life easier. And then the last thing maybe, or there's a couple more things. So we got this quaternion identity that sort of, if you think about the definitions, it's easy to know what this is. It's just a 1 in the scalar part and a 0 in the vector part. And sort of bootstrapping off of that axis angle definition that we did last time, if theta equals 0, and I have that like sine cos stuff, that's what you get, right? So that's pretty obvious. Okay, moving along, we've got this thing we call the hat map. This shows up in the kinematics when you want to integrate angular velocities. And looks like this. So we're going to define this, I'm going to write it like this, omega hat. This is, I take a vector, a 3 vector, and I just stuff it in the vector part of a quaternion with 0 scalar part. That's what it means. So we're going to similarly define a new matrix to write this as a matrix thing. So we're going to define a big H matrix that does the hat map. And, not rocket science. It's just a bunch of zeros and then an identity. So all it's doing is sort of lifting a 3-vector into a 4-vector with like a 0 on top. Easy enough. Weird defining, making up matrices stuff is just so we can take Jacobians. Yeah. So all I'm doing, right, if I look at that definition, omega hat equals like 0 up top, omega on the bottom. What I want to do then is I need a matrix that does that, right? So it's promoting the 3D omega into a 4D vector. So this matrix is going to be 4 by 3, and it's going to just literally take the bottom 3 as just omega. So that's just an identity block, and the top 0, right? So the top's just a row of zeros. Does that make sense? Yeah, not all of this is literally just, I'm looking at the definitions of these Quaternion things, and then I'm just inventing matrices to do the same things. So I can like write it as standard matrix vector math. So I can like do my usual like vector calculus stuff within, do the chain rule, do all that good stuff, right? So I can do optimization.
So the first one is 4x1, and what's the dimension?
You tell me.
4x4 with it?
No, omega is 3D, and omega hat's 4D. It eats a 3-vector and spits out a 4-vector. So it's got to be 4 by 3, right? Make sense? Cool. Okay, so so that's like just definitions, algebra, no big deal. So now I'm gonna we'll take a step back and talk a little bit about geometry, try to give you a little intuition for what's going on here. So geometry. Okay, so we know these things are 4D vectors, yeah? They're unit vectors. They have to have unit norm. So that means they, like the set of all these guys is like a sphere in R4. So it's called a 3-sphere because the surface of this sphere is actually 3D. It's embedded in R4, but it's just the unit sphere up a dimension. Like that's the way to think about it, right? Okay, so let's draw a terrible cartoon of this where I've got some Q here, say. Cool. Okay, so let's write that down. Q lives on a sphere in R4. This stuff gets a little trippy, but you can draw little pictures and get at most of this by thinking about it in lower dimensions. Okay, so what about Q dot? So if this thing's moving around, we wrote down the kinematics, last time, a little bit how to integrate, megas and stuff like this. If this is Q and Q's moving around on that unit sphere, where does Q dot live? Yeah, exactly. So Q dot is always tangent to the sphere. It lives in the tangent plane to Q, always. That makes sense? If Q can only move around on that surface, it can't have any component like parallel to Q pointing out or in or whatever. It's always got to be exactly perpendicular so that the norm stays preserved. So it's just moving around on the surface of the sphere. Yeah. So it's literally just, if you can imagine like having a sphere, at any point on the sphere, I can define a tangent plane, right? So Q dot always lives in that tangent plane somewhere. So the plane, like, okay, if I have a sphere in R3, normal sphere, what's the dimension of that tangent plane? 2D, right? So it's the same thing. It's just up, everything's up a dimension. So now I'm embedded in R4, but the surface is 3D. The tangent plane is 3D, right? So you can call it a hyperplane or whatever. The legit math words for this is differential geometry. This thing's called a manifold, the curved surface. That's the generalization of a surface, right? And this tangent plane thing, it's just called the tangent plane. The collection of all tangent planes to the sphere, right? So at every Q, there's a tangent plane, right? And at every different Q, there's a different tangent plane. So it turns out, right, if I think about the state space of a system, like the velocities are always in that tangent plane, right? So if you take all the Qs and all the Q dots, that whole thing together, that defines something we call the tangent bundle. So it's the manifold together with all of its tangent planes, like the union of all those tangent planes at every point. And that's like a big idea in differential geometry. That tangent bundle thing is also a manifold, it turns out. So you can think about it as like the unit sphere thing. That's like your pose or your configuration space. And then if you include the velocities, so like your whole state, right? The state space is actually the tangent bundle. That's sort of the way to think about this thing. It's a bunch of weird names of things, but there's some intuition in there if you have the picture in your head. Yeah, so well, it turns out, right, this whole thing's embedded in R4, but what's the dimension of the sphere? No, it's 3. Yeah, so the Qs, right, they are 4D, but they have a unit norm constraint. So that unit norm constraint actually takes out a degree of freedom. So just like the globe, right, like I can embed like a sphere in R3, but if I'm walking around on the surface, I'm in 2D, right? Like latitude and longitude for the Earth, right? Does that make sense? Yeah. So it's still only the surface here is only 3D, but it has this global structure where it's embedded in R4, right? But if you're like an ant walking on the surface, you're living in that lower dimensional space, right? Does that make sense? Yeah, cool. All right. Yeah, like I said, this is a weird thing that you gotta like really wrestle with to wrap your head around a little bit. So I don't know, it takes a while to. Okay, so let's write something down here. So imagine, right, we've got this point, and then I maybe have this like tangent plane at the point where like all my Q dots live. Right, any possible Q dot has to live in that tangent plane. Okay, cool. So that's that story. We did last time the kinematics stuff. Talked about it at least. So I'll just do quick here. So you've got this Q dot thing. This is a 4D vector that lives in that tangent plane, but it really only has 3 degrees of freedom, right? It's confined to the plane. And we can write this thing down in terms of omega, like our angular velocity, which is always a 3D vector. And so what's really going on with these Quaternion kinematics, which I think we wrote down last time, I'm just going to summarize again here. They look like this, and I derived these before. This is Q times omega hat, which looks like this, which we can write down in our sort of nice matrix vector notation as L of Q left multiplied by Q times H for the hat map times omega. Right. Okay. So what's going on there? If I actually like think about this for a sec, what that kinematics means geometrically is omega is always a 3 vector. What's really happening there though is I'm like writing down omega. Omega is in the body frame, right? And so what this is really kind of saying is omega in the body frame really means I'm writing it down always basically at like the North Pole of this unit sphere. And then what that kinematic equation is doing when I multiply by Q, what I'm basically doing is taking that omega that's defined in the tangent plane at the North Pole, aka the identity, aka in the body frame, and I'm rotating it down by Q to the current attitude of the body. That's what that means. That's like geometrically what's happening there. Does that make sense? I got that. It's a weird idea. So if I choose to write my angular velocity omega in the body frame, it's like the way to think about it here is I'm always writing it down in this like North Pole tangent plane. And then if I want to write down like, you know, Q dot, I basically have to like rotate that down to the current Q and then tack it on, right? That's what that says. So let's draw the little picture for that. So like maybe up here, you know, this North Pole tangent plane is where my omega is written. And then I sort of like rotate this thing down here and write it down in this new tangent plane over here, the tangent plane at Q. And this is like my Q dot. Does anyone, why does body frame equal identity here? Tangent plane at the identity. Does that make sense to anybody? What direction does Q rotate? It's always by convention, at least for us, it's body frame to inertial frame. So that literally says, right, like that equation is basically saying omega is written down in the body frame, aka at the identity. And then that kinematics equation is literally rotating it from like the body frame to the inertial frame, like the current Q, right? Okay. So let's see, that's that story. To give you a little more, I'm sure that, yeah.
So what value does omega represent? Is it roll pitch your dot or like,
No, it's
is it
not
just
that.
a
It's
math-
emphatically not that. Yeah. So first off, Euler angles are bad for you. You gotta get those out of your brain. This whole like roll pitch yaw stuff, it's actually like toxic and terrible. And unfortunately, it's like spoon fed to you at an early age when your brains are not yet fully formed. And it's like it's really insidious. You got to get it out of there. It's bad for you. So it doesn't mean that actually. If you go look up like this kinematics here that map omega into Q dot, there's a similar kinematic relationship between omega and Euler angle dot, like roll pitch, yaw pitch, blah, blah, blah. And it turns out those kinematics are god awful and they're full of singularities and super nonlinear and really bad. And this is like, kind of the gimbal lock stuff, all this badness. These kinematics are globally well-defined and bilinear and about as nice as you can get.
So
Yeah.
omega is just the matrix that makes the math work.
No, omega is what you measure with your gyro. Omega is your angular velocity. Yeah.
That's what I was.
Yeah, omega is sorry. Yeah, sorry if that was not. Omega is your angular velocity measured in the body. It's literally what you would get with an IMU attached to the robot spinning around, right? So that's like perfectly intuitive. So part of this is just like, okay, if I have a gyro measure omega and I want to like dead reckon on that, say I know my initial attitude Q and I have gyro and I just want to integrate that up and predict like my new Q after a little while, that's how you do it.
So it's just the integral of accelerations in XYZ direction.
No, it's not acceleration either. It's angular velocity. It's what a gyro measures, right? So like if I'm spinning, whatever, I strap this like gyro onto me, it's what that gyro says.
But in XYZ direction.
I mean, it has XYZ components. So if I were to write down like, the axis of the spin, right? Whatever that axis is in XYZ components in the body frame, that's what it is, right? Does that make sense? So if I'm spinning around, there's some spin axis I can define, right? That spin axis, whatever its XYZ components are in the body frame, that's it. That's what omega is. Does that make sense?
So if we have the Euler angles and then we differentiate and then we
Bad.
we get this.
No, you do not. Euler angles are bad for you. Again, stop thinking about. So this is very, very not intuitive. And unfortunately, the Euler angle stuff is actually far sketchier and worse and less intuitive than this. It's just that you got like spoon fed this like your freshman year physics class or something.
I'm not gonna use it, just a quick-
Well, no, so what I'm saying is like omega is actually completely unrelated to Euler angles. Omega makes sense. It's literally if I'm spinning and I like take the spin axis, that's a vector. Omega is a vector, right? It's like the axis of the spin times like, degrees per second or radians per second, right? That's totally well-defined, cool. Euler angles are not a vector. They're actually something much more evil. The way you know they're not a vector is if I take like, say I have a vector of Euler angles, like, and it says, I don't know, roll 90 degrees, pitch 90 degrees. If I like try to add two of those together, say I switch the order, say I have, roll 90, pitch 90. If I do roll 90, pitch 90, I'm here. If I flip the order and try to add those vectors, I'd get pitch 90, roll 90. It's a completely different answer, right? They do not add like that. They don't commute, right? I can't add them together so they're not vectors. Like vectors, if I take x1, x2, x1 plus x2, x2 plus x1, I get the same thing. Those add, that's the definition of a vector space, right? That they commute and they add and all that good stuff. Euler angles, if I were to write them down as vectors and try to add them together like I just did, it does not work at all. They don't add. The real thing that's going on under the hood here is this is what's called a Lie group. And the right way to think about these things is orientation attitude is a rotation matrix. It's a matrix. And like, if you think about it that way, matrices do not commute. We know this from like, sophomore linear algebra or whatever, right? If I have two matrices, Q1, Q2, if I do Q1 times Q2, or if I flip the order Q2 times Q1, I don't get the same answer, right? And that's exactly what's going on with this roll pitch versus pitch roll thing. Make sense? So thinking about it as Euler angles sort of gives you all these wrong sort of notions in your head. Angular velocity is a good idea. Omega works. That's a real physical thing. You measure it with your gyro on your IMU. That's it. That's what comes out of a gyro strapped down to your system, right? That's totally good. And what that is, again, is the axis of rotation times like the angular rate, right? Scaled by the angular rate. And that's a very well-defined thing. And that is a vector. That does add like a vector, behave like a vector. But if I try to integrate it, You can't actually. I can't do like integral of omega dt. That doesn't actually mean anything. It's like not a sort of good thing to do because you don't get this like additive stuff. The right way to do it, if I were to try to integrate omega into a quaternion or something, I get this. We talked about the rotation matrix version of this too, which looks very similar minus the 1/2 last time. The Euler angle version of this is really, really nasty and complicated. Has a bunch of trig functions and a matrix that can go singular and all kinds of bad stuff. Yeah, so it is not, the only way this matches up to like the Euler angle stuff is if you're only rotating about one axis. So if I have omega and it's only in the x direction and nothing else, then it does straight up integrate into, say, the roll, right? But if I have omega with component, you know, in x, y, z in general, it doesn't correspond to any kind of clean integral of Euler angles or anything like that. Does that make sense? I know I've been like real sort of, but yeah, the Euler angle stuff is like, so it frustrates me so much that like it gets taught so much so early and it just like pollutes your thinking forever unless you have to, it takes a lot of work to sort of dig your brain out of that hole. That's really sad. Yeah. No, it is globally singularity free, which is like one of the big reasons to do this versus the Euler angle stuff. And the real geometry here is like the way to think about this, the whole Lie group idea, the underlying geometry of rotations really is this sphere thing. And going back to the globe, we're going to do this in a sec, but I'll just give you the whole story. Okay, so remember, we're talking about this unit sphere thing. That is geometrically really what it looks like. And in terms of this sphere picture, Euler angles are basically latitude and longitude on the sphere. Just like when you have a globe, I can write down a 3 vector with like a unit norm or like a norm equal to the radius of the Earth, right? To like define a position on the Earth. That's good everywhere. If I try to write down latitude and longitude, what happens at the poles? So if I have latitude 90 degrees or whatever, I'm up at the pole. What's my longitude? Can you tell me the longitude at the North Pole? It's not defined, right? Because all the lines come together at the point. That's a singularity. So that's exactly what happens with Euler angles. When you get to a pitch equals 90, everything blows up because you're at the North Pole on this unit sphere. So if the way to think about it in your brain is the underlying geometry is this sphere picture. Euler angles are latitude and longitude. Latitude and longitude on the Earth has singularities at the poles and stuff. Euler angles have singularities at pitch equals 90 and stuff like this, right? Same thing. And just like you could write down a position on the Earth as like a 3 vector with a norm constraint to make it on the surface of the Earth, that's all we're doing here. 4 vector with a unit norm constraint. Hopefully that gives you some more. Yeah.
Is there a reason you need 4 dimensions to accurately describe rotation?
Yeah, it basically comes back to this sphere idea. So another way to think about this, using the analogy like the globe thing, you know about map projections? Like if I take the Earth's a sphere, I try to write down, like if I were to try to draw a map of the entire Earth, like out on paper, I kind of can't. I can draw local maps of like small chunks, but if I were to try to write down the whole globe, like on a flat map, I actually can't do it. And there's this whole thing about map projections where you have all these weird ways of basically like trying to unwrap the globe. And any way you do it, you run into trouble somewhere. You run into like some singularity or some like point at infinity or whatever. And there's all kinds of, it basically comes down to this like basic geometric fact that I can't like take a sphere and like unroll it onto a flat plane, right? So like literally if I'm trying to use 3, so there are only 3 degrees of freedom, right? But it's this unit sphere thing. So if I were to try to write it down with only 3 coordinates, i.e. Euler angles, which are like latitude and longitude, what I'm really trying to do there is like unroll the sphere onto like the globe analogy, right? Is latitude and longitude on a globe, which is easier to think about. I can write it down using 3 vectors, like to, you know, be on the surface of the sphere. Or if I'm using latitude and longitude, what I'm implicitly doing there is trying to like unroll the globe and write it down on some flat 2D plane with X and Y axes equal to like latitude and longitude, right? That's like what I'm trying to do. And that has to break somewhere. There's like no way to do it globally. And this is like a core idea from like differential geometry manifolds. Like I basically can't unwrap the sphere and have it work everywhere. There's going to have to be some points where it kind of goes bad and stuff like this. I don't know. There's lots of ways to think about that, but that's like at its core, it's this idea of like, you can't globally unroll a sphere and like write it like and smush it onto a plane and have that work out everywhere without having some points where you either have to cut it or you have to like have it go to infinity or some weirdness, right? You can't just like have a 1-to-1 map that's good everywhere. In the attitude case, there's a paper from the 60s by a guy named Stulpenagel, where he proved mathematically that there's no globally smooth and non-singular 3-parameter attitude representation. So those are the words. You can choose to have it, you can use 3 numbers, but somewhere it's either got to have a jump discontinuity or a singularity. That's the trade. If you go up to 4 dimensions, then it can be smooth and nice and continuous everywhere. And that's why we do this. Rotation matrices are also smooth and nice everywhere, but they're 3x3 matrix with a lot more constraints and they're more annoying to deal with. So these are like the way to go. These are using computer graphics, aerospace, robotics. These are like the thing to do if you want to do like numerical computation on rotations. Okay, yeah.
What's the difference between, I mean, if you take a quaternion like unit vector to the scale, why not just take it as like a vector with some yeah.
It's a totally different idea. We're gonna have to take this offline. I'll show you what you're talking about. What you're talking about is like a 3-vector with some scaled length thing.
Yeah.
These are actually related. Those are called axis angle vectors. You can write those down, but they have singularities. They have kinematic singularities. I'll show you why. It's actually a really nice geometric story there, but I don't want to get into it right now. Yeah.
Could you talk a little bit more on body frame?
Oh yeah. Okay. So I have like my robot, whatever, it's rotating around. The definition of attitude is the rotation from some, so the definition of a rigid body really like comes down to, it has, I can take this thing and I can slap a coordinate frame on it that's attached to the body, but I get to make it up, right? Okay, so now I have this frame attached to my robot, whatever, my drone, and then I have some world frame that's like that I painted on the walls of the room or something, right? So the definition of attitude is the rotation from the body frame to the world frame. That's the definition. I can write it as a rotation matrix. I can write it as a quaternion. If I'm a sadist, I can write it as Euler angles, right? That's it. So that's the definition. It rotates. If I took a vector in the body frame, say like a camera bore sight, my angular velocity from my IMU, whatever, these are all defined in the body frame, right? So I took that vector and I wanted to like know what it was in the world frame. I would rotate it by my quaternion or rotation matrix that defines my attitude, right? So if I'm like, this shows up all the time in robotics. Like I have a camera bolted to my robot. I'm observing these things in the camera frame, it's in the body frame, it's in, you know, and I want to like compare that to like known features in the world frame. I rotate stuff, right? So this is exactly where this shows up. It's like everywhere, right? Pose estimation, control, it's super pervasive. So it's really good stuff to know. Yeah.
And just to understand what the quaternions, because they are vectors, they have all these properties.
Quaternions are not vectors either.
Okay.
Yeah, and rotations are not vectors. That's the key thing. So no matter what I do, quaternion, rotation matrix, Euler angles, never a vector. It is by definition not a vector.
Okay, then I'll hold my thought. I want to hear more.
Yeah, okay. So that's like the key thing you got to get through your head. The best way to think about these things is just think about them as rotation matrices. If you think about them as matrices, you won't go wrong, right? They compose via multiplication. They don't commute. You can't just add them together. Like thinking about every time you see a rotation or an attitude or a pose or whatever, just in your brain, quaternion, doesn't matter what, think about it as a matrix. Think about it as a rotation matrix. You got to multiply them, blah, blah, blah. That'll get you the right idea. Okay. Yeah, then we really got to get moving again. Sorry? The half. So yeah, there's halves that show up all over this stuff when you talk about quaternions. It's a little subtle. Stick around after and I'll like this. We did it in the previous stuff and the videos and like Kevin's stuff from last time we derived the kinematics. There's actually a really nice geometric picture for why that I'll give you guys the little post lecture hints on this if you want. It's kind of fun, but yeah, for now we got to keep moving. Sorry, yeah, run out of time. Okay, so here's the next thing I want to do is hopefully give you some more intuition for this. We're going to do the like 2D planar version of this, which you've probably seen before and didn't think about it. So it turns out all this quaternion stuff in 3D has exactly equivalent analogies in planar 2D land, where you think about we only have one axis of rotation. You can either write that down as a theta, or you can write it down as a complex phasor or 2D unit vector. The complex phasor is exactly the same thing as the quaternion in R3. They're just like, the quaternion is the up a dimension 3D version of a complex phasor in the plane. So we're going to do that right now. I'll show you exactly how they match up. And that's what you want. Okay, here we go. Hopefully this makes some sense. So yeah, who's seen like phasors, complex numbers? You've seen this before, right? I'm not like, otherwise it doesn't really make sense for me to do it. But assuming you took some EE class, you did complex something, you've seen this before. Okay, so the idea, right, is I got a complex plane or whatever. I mean, you don't have to think about it as complex numbers, but that's usually where you see this stuff. So let's say, I don't know, I'll just call this X and Y, or you can think about it as real and imaginary or whatever. Got some vector, say V here. And I can measure this guy, say this V is a unit vector. I can think about it either as some theta here, or as its X and Y components. And I can write this guy down as, V equals cos theta plus I sine theta, if I'm thinking complex phasor. Or I can think about it as, cos theta times X hat plus sine theta times Y hat, whatever you want, right? Either way, it doesn't really matter. And so this is your X component. And this is your Y component. Okay, and so just looking at that, if I were to write down, this thing, if I were to stack it up as a, vector, I've just got this, cos theta, sine theta thing. And just looking at that, it's super obvious that if I take V transpose V, I'm going to get cos squared plus sine squared. That's got to be 1, right? So that, everyone cool with that? Checks out. Just from, okay, awesome. So now what we're going to do is take the time derivative of V. Okay, so I'm going to write down V dot equals, so I'm going to write it in terms of theta. I'm going to chain rule through this. So I've got partial V partial theta times theta dot. Everyone cool with that? Okay, and now we're going to just write that out in some more detail. So partial V partial theta is minus sine theta cos theta. And this thing is times theta dot. I'm now going to write this down. I'm going to like kind of cheat a little bit. It turns out what the guy is just one column of the 2D rotation matrix, which I'll now write out in full. And now if I write it like this, it's sort of obvious that what's going on here is, okay, so first this is a 2D rotation matrix. And then this guy is like my hat map, where I took the omega and stuck it as the vector part of a quaternion. Here, I take the theta dot, stick it in the imaginary part of my complex phasor, complex number, right? So vector part equals imaginary part, scalar part equals real part. There's this analogy, whole analogy with complex numbers and quaternions. Like one way to think about this is quaternions are just generalizing complex numbers from the plane to R3. And so that's sort of, this guy is like our sort of like 2D hat map. And I can write down like, so now looking at it like this, what's going on here, right, is I'm taking this, if I have my XY plane or real imaginary plane, whatever you want to call it, let's say I've got my V over here. I've got my theta. This is kind of a bad drawing. Sorry, let me help myself to draw a little better. Draw the circle first. So, okay, so I've got my V here. I've got my theta. So the way I wrote theta dot, it's basically this guy. It's pure Y component, right? And basically it's defined over here at the identity here in this complex number land is just X, right? A 1 in the X direction. So if I write this as the tangent at the identity, just like before, I'm going to get this guy, theta dot, which is just a Y component, and it's sort of rooted at the identity, which is along the X axis there. So this guy's theta dot. And then what my rotation matrix is doing is taking that theta dot vector and rotating it over to where V is right now, right? So we're over here. So this is V dot. It's literally just taking that theta dot guy, rotating it by theta. That's what that rotation matrix is doing to give me V dot, which is the tangent to V at where V's at right now. Does that make sense, everybody? So this is like the complex number 2D plane version of this stuff. It's exactly the same. The intuition's all the same, just up a couple dimensions. Okay, cool. Let me write that down. Okay, cool. All good on that stuff. I've given you, I think, about as much as I can with this. You gotta like try it, wrestle with it, think about it some more. And yeah, if you want to talk more about this, come up. There's more. I don't know. I've obsessed with these things for a while, as you can probably tell. Okay, so that's sort of giving you some geometry, some intuition. Now we're going to talk about differentiating these things, doing some optimization. Okay, so here's the things you got to know. Two key ideas. The first one is that the derivatives, if I'm talking about differentiating these things, these quaternions, just like angular velocities, q dots or whatever, whenever I take a derivative of one of these things, the derivative has to live in that tangent plane. Make sense? Obvious, right? Tangent equals derivative. So anytime I'm taking a derivative of a quaternion thing, they're always sort of, they're 3D and they live in this 3D tangent plane, just like omega, right? Just like angular velocity. So that's number one. And then number two is that rotations compose by multiplication, by quaternion multiplication, rotation matrix multiplication, right? You don't add them like vectors. So literally, it's just those two facts. I'm going to take those two facts. I'm going to take the algebra we have, hopefully a little bit of that geometry picture in your brain, and we're just going to like turn the crank on this and figure out how to do standard matrix vector derivative stuff here, how to take gradients with respect to a loss function that's got a quaternion argument, how to take Jacobians of dynamics with quaternions in them, how to write all that stuff down, how to write your A and B matrices down, how to write your cost functions down and diff them, and then how to do Newton's method on top of this. That's what we're doing the rest of the lecture. Super straightforward. So here we go. Okay, so first thing is we need to have an idea of an infinitesimal rotation, i.e. like rotation gradient, or like the thing that your gradient multiplies, I guess. So we're gonna write this as like a little delta Q. And remember like the axis angle definition, which is where those factors of 2 kind of really show up. This is it. This was from the last sort of lecture and Kevin stuff. Hopefully this is familiar. Otherwise, go back and look. So this is the angle of rotation is theta, and the axis of rotation, which is a unit vector, is A. And that's the scalar and vector parts, right? So if I have a small angle and I make a small angle approximation of that guy, what's going to happen? Cos theta is 1 and sine theta is just theta, right? So I'm going to get 1/2 a theta down here. And that a theta thing, if I take the unit vector axis times the angle, that's called an axis angle vector. And we can just write that as like just a 3 vector, and we're going to use those a lot. So we're going to just write that down as 1, and then we're going to call that axis angle thing phi. So that's a 3D vector that has units of radians. And what it is just like, if I'm rotating, it's the axis of rotation. And its length is equal to the angle of rotation that I rotate about that axis. That's the closest thing to like the derivative or the integral of omega, right? It turns out actually, if I have an omega and it's constant about the same axis and I integrate it, I get phi. So phi, you can think about phi kind of sort of as that's the closest thing to like integrating omega from your gyro. Okay, cool. So this guy is a small axis angle vector. Okay, so if I keep going here, I can write down that thing as an identity quaternion, right? So 1 in the scalar 0 vector part plus this guy with 0 up top and just the phi in the bottom. And this is equal to identity quaternion plus 1/2 times my hat map times phi. Okay, algebra. Okay, now so this is like, if I were to do a bunch of, say, gradient-y stuff, if I want to take a gradient step on like my quaternion, the gist of this is what I want to do is actually take a step on phi. I want to calculate my step as a phi. And then once I have that phi, what do I do with it? Say I linearized about some q, I compute the step. I don't add it back on. Like, remember when we did Newton's method before, I compute some step delta x and then I add it to my x. Here I can't add them, I got to multiply them. So the move is I'm going to take that phi, I'm going to convert it back into a quaternion, a delta quaternion, and then I'm going to multiply it on instead of add it on. That's it. So this is just the composition rule, right? So I'm going to take that thing and then I'm going to compose it with q. So I would get something like, say, q prime equals q times delta q. And I can write that down as, in terms of my matrix stuff, as, say, L of q, so left multiply, right, by that q. And then if I write down my sort of delta q stuff that I just did, it's something like identity plus 1/2 h phi. And if I just kind of expand that a little bit, that actually, the first part is just q times identity. So that just gives me back the q. The second part looks like 1/2 L of q times h times phi. So this looks a whole lot like q plus some delta thing, like the additive thing we're used to seeing, but it's got this extra Jacobian on it. And this shows up a lot. So we're going to make some stuff up here. We're going to call this thing, we're going to give this its own name, g of q, and we're going to call this, so this is a 4x3 matrix because it maps a 3D phi into a 4D quaternion. And we're going to call this guy the attitude Jacobian. Okay, that was a little fast, but the punchline is actually really clean and nice. So let's do, there's one note before I get to the main punchline. This note is, so here I'm using this like phi thing. I told you it was an axis angle vector. Turns out it actually doesn't matter. You can interpret it as being axis angle, Euler angles, if you're evil. What else? Vector part of the quaternion, Gibbs vector, modified Rodriguez parameters. There's lots of these things, but basically it turns out that when I go linearize the rotation stuff and do this 3-parameter thing, it turns out any 3-parameter rotation choice I make, whether it's axis angle, Euler angles, whatever, it turns out they all linearize the same up to some constant. So here I got this 1/2. If I did this with, say, I don't know, Euler angles instead, it might be a 1 instead of a 1/2, whatever. Modulo some constant out front, they're all the same. So it doesn't actually matter whether it's Euler angles or whatever here. So you can think about that phi as anything you want. It's some little rotation is the key idea. And it turns out when I'm talking about little rotations and linearization, they're all the same. Doesn't matter. That's not obvious until you go work it out. But if you try it, you can actually write this out for Euler angles if you want to and see that it comes out the same. So we can use any 3-parameter rotation, representation that we want for phi. They all linearize the same up to a constant. So what we're going to do is there's several choices. So here's like a few of the options you could make, you could choose to use. If I were to use axis angle, which are kind of the ones we talked about, that would look like this. To map it back into the quaternion, I would get something like norm phi over 2 being the angle, and then like the axis would be like phi over norm phi, and I'd have, sine norm phi over 2 for the angle, something like that, right? Or I could use the vector part of the quaternion, and I could write it like this, where I just sort of compute the scalar part using the unit norm constraint. And then this guy's just down here in the vector part. Or I could do this other thing that we call Gibbs vectors or Rodriguez parameters, which is very similar to the vector part of the quaternion thing, but looks a little different. Looks like this. We rescale the whole thing. So these are some options. Or you can use Euler angles, but those are really gross, as we've already said. So this is axis angle. This is vector part of Q. This is Gibbs or Rodriguez vector. So we're gonna, you can use either one of these, any of these. It turns out we don't generally use axis angle because the transformation there is a little nasty and has trig functions in it, which is kind of annoying. Vector part of the quaternion is easy, and Gibbs Rodriguez vector, both easy. They're about the same. They're like algebraic, whatever. Just looking at this, actually, it's kind of clear, right, that like at least for the second two, that this transformation, if I linearize this transformation, it's the same for all of them, right? If you look at it, the non-linearity in there is all second order, right? So I got like phi transpose phi stuff, or I've got sines and cosines, but all the non-linear stuff, if I linearize that thing, kind of, they're all the same. Cool. Oh, I missed some paths. It's to first order, it's like this axis angle thing, has units of radians, axis of rotation, blah, blah, blah. The like the nonlinear version is slightly different. They're like scaled. They're a little different, right? All these linearize the same though. Phi over phi norm is always the axis of rotation. It's just that the norm in general is scaled by some nonlinear thing. It turns out in the vector part of Q thing, it's scaled with a sign nonlinearity, which is kind of obvious if I look at the axis angle. Turns out the Gibbs one is scaled by a tangent nonlinearity. So whatever. There, but yeah, it's not obvious. You can work it out with some trig from the first one. Okay, cool. So for sort of ease of use and stuff, for now we're going to use just the vector part of the quaternion, so that middle one, because it's easy, but they're all kind of the same. I think Kevin used the last one in his stuff for some of the discussion. Okay. Let's see. Okay, so now we're basically ready to differentiate functions that involve quaternions. That's sort of the main trick. And here's the punchline that's really awesome. So the punchline is, if I have any function f of q that I want to take its gradient of or whatever, all I have to do is take its Jacobian gradient, whatever, the way I normally would, as if q were just a vector. And then all I got to do is slap on this attitude Jacobian. That's it. End of story. Take the derivative as usual, your normal vector calculus stuff, slap on attitude Jacobian on the right-hand side. And now you're good. And now you've got like the right sort of like 3D tangent plane derivative thing. So let's, I'll show you how this works a little bit. What's that?
The A part, A before scientific, that you wrote earlier, is more general, right? Like where A is one, because taking phi by magnitude of phi.
So A is literally phi over norm phi always.
Unit vector.
A is a unit vector. It's a 3D unit vector that's defining the axis of rotation. And then the angle of rotation is say theta. Or basically the way to think about this, if I took that axis and multiplied it by the angle, I would get this axis angle thing, right? which is phi, right?
Just wanted to know A.
Yeah, A is by definition unit vector. And like this phi thing is A times theta, or in general, A times some nonlinear function of theta. But that's what all these are. Okay, cool. So we're just going to plug these attitude Jacobian G things in the right places. And I will show you all the useful examples of this real quick. Okay, so first one is if I have some f of q that's eats a quaternion and spits out a scalar. So here, think loss function, right, or cost function. And we'll show you an example of this in a little bit. So this is gradient of a scalar valued function. So all I got to do is, so I'll use the grad notation like this guy to mean the like 3D derivatives that we actually want. And I'll use the partial notation to mean like the naive, derivative, as if you were to just differentiate it as if Q were a normal 4D vector. So like basically what you're going to do is this. Oh, by the way, does everyone know this Blackboard bold H notation means quaternion? It's H for Hamilton, who invented these things. Just like Blackboard R is for reals, Blackboard C is complex, Blackboard H is quaternion. And it's H for Hamilton, who invented these. Same guy as Hamiltonian, etc. Okay, so we got this. And there's a few ways to think about this, but like one way to think about it is this is like df dq and then like df dq d phi, right? And where I mean dq d phi is diffing through those expressions there. Take your favorite one; they all linearize the same, as I said, right? Doesn't matter. So dq d phi, and this thing then ends up just being like your df dq, again, like the naive derivative. And then this dq d phi thing is this attitude Jacobian. Cool. So literally take the gradient, slap on the attitude Jacobian. Life is good. I can do gradient descent or whatever I want, as usual. Okay, so that's gradient. The next one that shows up a lot for us, so this would be gradient of your cost function. The other one we have to think about all the time in our business is dynamics, where it's a function that eats a quaternion and spits out a quaternion, right? So if I'm thinking discrete time dynamics, like my drone flying around, it eats a qk and spits out a qk plus 1. So now I have to do this on both sides. And in particular, it's a little subtle. On the right-hand side, you're doing it with qk. On the left side, you're doing it with qk plus 1. So the arguments of the g's are different on both sides, but it's otherwise, here, let me write this down. So this guy's, say, from h to h. Think dynamics, discrete time dynamics. So this is a Jacobian of quaternion valued function. So the way this guy works is, remember, we're basically going to play the trick on both sides. So what we're finding on the output side is a phi prime, and it's you're going to use the attitude Jacobian on both sides. So here it's like computed about on the output quaternion, and it gets transposed. And then over here, it's your regular naive Jacobian. And then, the stuff on the right is the same thing. Okay, so the way I think about that is if I have dynamics and I'll compute the A matrix in the normal way, that's partial F, partial Q. And then on the right-hand side, I slap on this attitude Jacobian at, QK. On the right-hand side, I want to do this on the output. So if the nominal output is like qk plus 1, I evaluate g at qk plus 1 and slap it on the output side, and it gets transposed. Cool. That's it. Straightforward. And this thing we're going to call grad f in here, right? Or we'll use this notation. And this guy in this example, right, this is 3 by 3. So my naive Jacobian would have been 4 by 4 here, but then I slap this on both sides, it's 3 by 3. There's a good reason to do this, which we'll get into, like, I think probably next time we're going to do LQR with this. So the idea is this one's transform the input, and this one is transforming the output. into like this little 3D land. Okay, let's see, what else is there? Cool, I think that's that. And then the last one is Hessians, right? So if I have, say, my cost function, similar story as before, right? Now we're just talking about the Hessian. So this is like your loss function, whatever, eats a quaternion, spits out a scalar. We're going to write this like this. It's d squared f of q. This one is a little, this part's sort of obvious, and you would kind of expect. I'm just going to smush the Hessian on both sides with this g. But there's an extra term that shows up that's less obvious, and I'm just going to show it to you. So this is a 3x3 identity. This whole thing's a scalar, if you think about it for a sec. And where this is coming from is the partial g, partial q. So this is coming from like the derivative of the attitude Jacobian. It's like that second derivative stuff. So that's pretty easy. Plug and chug. I won't derive that, but you can figure this out. It's not hard. Okay, cool. So now we can basically take all this stuff we just did and just do Newton's method, do gradient descent, do all this stuff we normally do. We can also do Dirk-Hall and DDP and LQR with this, which we're going to do next time. But today, I'm just going to show you doing like vanilla Newton's method with this on a classic problem. So let's do that. First, I got to introduce the problem now. So now we can do Newton's method and DDP and SQP, all the acronyms with quaternions. And so, okay, so the example we're going to do with this is an extremely classic pose estimation problem called Waba's problem. Has anyone heard of this before? Nobody. All right. Cool. So the idea here is if I have a bunch of vectors collected from a camera to like known features in the environment. So if I have like a map of the room and I have a bunch of features on the wall, say that I know, right? Whatever, like tags, something, fiducial markers, whatever. I know where they are in the world frame from a map. And then I observe them with my camera and I get unit vector directions to them in my body frame from the camera. That's the problem. So I have those vectors, unit vectors. I know what they are in the world frame and I know what they are in the body frame. I know what they are in the world frame for my map. I know what they are in the body frame for my camera observations. So I have a collection of vectors where I have them both in the world frame and in the body frame. And the problem is, okay, given all those vectors, I want to figure out what my attitude is from the vectors. So we're going to write that down as a least squares problem over a quaternion. This is a total classic in like aerospace. This was posed actually as a challenge in a journal in like the early 60s. And it was solved as like, I don't know, it was given as like this kind of challenge problem. And it's known as Waba's problem after the statistician who posed it originally. Okay, so given a bunch of vectors to known features in the environment, determine the robot's attitude. Okay, so, right. Called Waba's problem. So I basically think about it as I have a map and I know where these things are on the map. So I know like, so if I know my position, right, this is the scenario, like assume I know my position and I have a map and I have all these things, these features out in the environment. So if I know where I am and I have this map, I know what the world frame vectors are from my location to the features, right? just from knowing where I am and knowing the map, right? So I have all these unit vectors that would point from my location to these features in world frame coordinates. I have a camera on the robot. I look around, I see the features, blah, blah, blah. I compute using, say, a camera intrinsics, whatever, but I, forget all that. I can compute these unit vectors now in my body frame, knowing, from the camera observations, right? So I have this set of vectors. I know what their directions are in the world frame from the map, and I know what their directions are in the body frame from the camera. And I want to take that set of these vectors. So I know they're the same vectors, but I have them written down in 2 coordinate frames. I have them written down in world coordinates and body coordinates. And I want to take those sets, those 2 observations of the same vectors, smush them together, write all these squares loss function down, and figure out what my attitude is, my attitude quaternion is from those vectors. That's the problem. So I'll write the math down, but that's kind of the idea. Here's the math. So we're going to do min over q of this cost function. And here it is. Sum over, say, we'll do this as k equals 1 to m. So I have m vectors, and it's exactly what you'd expect. So if I have the version in the world frame, which I'm going to write with an n superscript, it's got to be, it should match as closely as possible. This is going to be the rotation matrix, big Q, computed from the Quaternion, which we did last time. Rotation times the body frame version, right? So the rotation is from body to world coordinates. XBs are the body frame ones that I get from my camera. XNs are the world frame ones that I get from my map. And that's it, right? Q times XB should give me XN. I write down a least squares loss on that and minimize it. That's it. And I'll like rewrite this slightly as this residual function, R of Q, 2 norm squared. So the thing inside the 2 norm squared is, we're going to just call the residual. So the difference between those body inertial things, right? And then these are known vectors in the world frame. And then these are observed vectors in body frame. So this would be like from a map. This would be like from a camera. Cool. Okay, so let's see what else is there to say about this. X Kn and XKB are unit vectors. They're the right way to think about them, right, is their directions. And then this residual guy, R of Q, is gonna be, if I were to like write the whole thing, right, it's like X1 in N minus Q times X1 in the B frame, blah, 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 all the way down. Okay, so this is R. And now this thing, right? This is a function of a quaternion. It spits out a big vector in Rn actually, right? I'm going to write down this guy's Jacobian. So we're going to write this grad R of Q. This thing is 3m. So I have m observations of these 3D vectors. So this guy's 3m by 3, because I'm going to take this quaternion derivative and like play my trick to make it 3D. So if I write this out, right, it's just partial R. Oh, it's nah. This guy is normal naive derivative with respect to the quaternion, like as treating as a vector, times attitude Jacobian. This is 3m by 4. This is 4 by 3. That all works out dimension-wise. So that's like basically it. And then what we're going to do is apply the Gauss-Newton method to this thing and minimize it. So let's write that down. Maybe I'll write down the classic Gauss-Newton thing first as a quick review. So that guy's 3m by 4. And then, yeah, that check out. Yeah.
The dimension of Q is 3 by 3 here.
The dimension of Q,
Yeah.
big Q is 3 by 3 matrix. Yeah.
Usually, like, when we take homogeneous system and there's translation, but
We're not talking about the translation part here. This is just the rotation part. Yeah, yeah. So this is like the sub problem that's only concerned with the orientation, which is the WABA problem, the classic thing. Okay, so let's just do a quick review of Gauss-Newton. We talked about this before when we did like DDP and SQP stuff, but just in this context of least squares, like just as a quick aside, make sure we're on the same page. What we're trying to do is this thing. I'm trying to minimize the sum of the squares of my residual vector. And I can equivalently write that as just R transpose R. So if I go to like write down my Newton method on this guy, I've got dj dx equals R of x transpose times dr dx. And if I write down the Hessian d squared j dx squared to do my Newton thing, I'm going to get a term that looks like this. Right, it's like the residual like Jacobian thing kind of squared. And then I'm going to get an additional tensor term. In this case, it looks like this using our like Cronvec stuff that we talked about a whole bunch before. And basically the idea is we're just going to throw this part out to get Gauss-Newton. And so if I put all that together and write like the full kind of Newton step thing, I'm going to get d squared j dx squared inverse, like my Hessian thing, times grad j, my gradient thing. We're going to approximate this as dr dx transpose dr dx inverse dr dx transpose R of x. Cool. This is also like the, what do we call this? Normal equations, or what else is this called? This is also called pseudo-inverse, right, of the Jacobian. Okay, so these are all kind of the same thing. So that's Gauss-Newton. Oh yeah, d squared vec of R dx squared. So that's like the Hessian of the residual written out using our, because otherwise that would be a third rank tensor. This is like our vec tricks for doing tensors. Okay, so finally, this Gauss-Newton thing for the WABA problem that we just did. Here we go. So we're going to take an initial guess. Q, get some Q naught, just like we always do. We're gonna, I'll write this down like pseudocode style. We're gonna compute our gradient, which again is the standard one times the attitude Jacobian. And the reason we do this stuff too is this is nice because you can just auto diff this, right? If I do forward diff, I get the first thing, partial R, partial Q, right? So I can do forward diff and then I just slap on these attitude Jacobians wherever I need to, and then this all kind of works out. So I do that. Now I'm going to compute my step, which is a Newton thing. We're basically going to compute all the Gauss-Newton stuff using, again, the stuff up there with the attitude Jacobian kind of plugged in. Then when I update my Q, I'm going to do the multiplicative thing instead of adding, right? Like we talked about. So I'm going to take the phi that I get out and plug it into this, assume it's like the vector part of my Quaternion and multiply it on. Multiplicative update. So basically the tricks are I apply the attitude Jacobian thing when I compute my Jacobian. Then I just do the normal Gauss-Newton step, but that's going to give me like this phi update. And when I take the phi, I turn it back into a full quaternion, a delta quaternion. I multiply it on to my like last one, right? And then, you know, in general, I would maybe do a line search here. Like I probably should. But you know how to do that already. No big deal. And then we'd sort of like do this whole thing while say our error is above some tolerance. Cool. Okay, that's it. Everyone, any questions about that? It's normal Gauss-Newton. All I'm doing is playing the attitude Jacobian trick on the Jacobian. And then I'm playing this multiplicative update trick to update the quaternion instead of adding, right? Because I can't add rotations. It doesn't make any sense. The right way to do it is multiplication. Okay, cool. So now we'll do it. Get the code. Where's the code? Cool, code. All right. Zoom in a little bit. Okay, cool. So what's in here? This is all the usual boilerplate. Okay, here's the hat map. This is the like skew symmetric cross product matrix thing. There's my L thing that does left quaternion multiplication, my R thing that does right quaternion multiplication, my T and H, this guy does my conjugate, this guy does my hat map. So here's G, my attitude Jacobian. And then this guy is the function that takes a quaternion and converts it into a rotation matrix. This is in the last video / Kevin's video stuff and notes. It's really easy to derive it. So go look up that if you need to. So here we go. We're going to do the Gauss-Newton thing. I'm going to take I'm going to generate just a random quaternion. It turns out this is actually a legit way to sample quaternions. Like it's statistically legit and everything. So if you need to sample random rotations in your life, it's actually a very reasonable thing to do. You sample a random 4 vector and then just normalize it. And it turns out if you like sample from a Gaussian, this is still Gaussian. Sample from a uniform distribution, it's still uniform, blah, blah, blah. It sort of stays nice. Fun fact, if you need to sample random rotations, that's a good way to do it. So I can sample a random quaternion like this, normalize, and then I can just turn that into a rotation matrix. That's slick because like, how do you randomly sample a rotation matrix? Not obvious, right? So this is a good way to do it. Okay, so now we're going to generate some random vectors. So these are going to be my, say, inertial frame vectors. I'm going to just randomly generate 10 vectors. And then I'm going to normalize them so they're unit vectors. And then I'm going to take my truth rotation and rotate them into the body frame to generate my like observations, right? And I could add more noise to this or whatever if I wanted to, like, you know, to mimic a real sensor or whatever. We won't do that right here, but you know, you can obviously do that. Here's my residual function. So it's inertial frame minus Q times the body frame one. That's it. Super easy. Its function eats a quaternion, spits out this, like, in this case, 30-dimensional output, right? So it's 10 vectors, they're 3D. Okay, I'm going to generate a random initial guess for my starting quaternion to start out with my Newton's method. And now here's the Gauss-Newton thing we wrote down. So here's my phi. I'm going to do some iteration count stuff. I compute the residual. I'm going to forward diff that residual with respect to Q, slap on the attitude Jacobian to get my like grad R thing, do stock, you know, Gauss-Newton step on that guy. Then I'm just going to put that back together. And so this is like Q times that unit quaternion lifted thing, right? I take the phi, convert it to a quaternion, multiply it by my previous Q to get the new Q. That's it. Cool. So let's run that. How many iterations? 6 iterations. Like, seems reasonable for Newton's method. You know, it's a nonlinear problem. Let's see what we got. So yeah, it matches to machine precision because I didn't put any noise on anything, right? Let's run this a couple more times. I want to show you something weird that'll happen if we run this a couple times. Yeah, okay, so that worked. Gotta let the random seed help me out here. Still happening. Okay, here we go. So this doesn't match. What's going on? Why doesn't it match?
It's because like there's two.
Yeah, exactly. You did it with your arms and I knew you knew what it was. So, so what's going on here, right? This is from like previous stuff. I didn't do it today, but quaternions double cover the space of rotations. Q and minus Q give you the same rotation matrix. So here, Newton's method is local. It's gonna converge to whatever one is closest to my initial guess. So depending on my I was just giving random initial guesses here and then running it, right? So Q and minus Q both minimize the loss here. And like totally, they give the exact same answer because they give me the same rotation matrix, right? And it's also super obvious in here. I'm actually in my loss function, I'm converting this to a rotation matrix. So Q and minus Q give the exact same rotation matrix. So depending on where I choose my initial conditions, basically which hemisphere I'm in, I'm just going to go to the closest one. So here, trying some random seeds, I landed in a different one. So here I did Q minus Q true, and I got something big. If I do Q plus Q true, let's see what happens. Yeah, so that's 0. Does that make sense? So this thing will give me Q or minus Q, depending on where I guessed to start out with. Generally, this is fine and doesn't cause any problems. But if you are like a little bit naive about how you, for example, write down your loss function or write down your error in your feedback controller, you can run into problems because of this. There's this famous thing called the unwinding problem. If you write down a really naive feedback law on a quaternion, and my state estimator, like say I'm trying to do feedback on Q, and I have like a Q ref, if my state estimator all of a sudden flips it around and gives me minus Q ref, you can have your controller wrap you around like 2 pi for no reason because of this thing. So this is like a fun fact to be careful of. There are good ways to deal with this. It's not a big deal in practice. You just have to be a little smart, but that's kind of it. Okay, that's it. Thanks everybody.